And now a fun geometry contest problem, AIME 2016, AIME 2, question number 5. Triangle ABC0 has a right angle at C0. Its side lengths are pairwise relatively prime, positive integers, and its perimeter is P. Let C1 be the foot of the altitude to AB, and for n greater than or equal to 2, let C sub n be the foot of the altitude to C sub n minus 2b in triangle Cn minus 2, Cn minus 1b. The sum of all of these will then equal 6p. And so what happens is this. Let me draw the original triangle. And I have A, I have B, I have C naught. In here, we're going to keep on making altitudes to the hypotenuse. And we know that when we do altitude to the hypotenuse, we get, we're going to create a geometric sequence that we're going to sum up. So an infinite geometric series. Put a little dot, dot, dot in there. Well, that's quite a dot. Okay, so in here, I know I'm going to have a geometric sequence, and that's nice. I can use that, the infinite sum, which is what this is going to eventually be, is going to equal the first term times 1 over 1 minus the common ratio. So I can figure this stuff out. I got it. Next thing, if they're positive integers, that means that they must be a Pythagorean triple. So for instance, and this is not the final answer, but if I had this be 3, this be 4, and this one is 5, then I can look at this triangle and this triangle, this triangle and the full triangle, and get the ratio 3 over 5 equals x over 4, and I will get x is 3 times 4 over 5. 3 being the original short leg, this is my new short leg of this triangle, and 4/5 being the common ratio. If I continue, the common ratio will be 4/5. So I could use this to move on. But this will not give me this value. So in this, the first one here is 12/5. I'll just go through and say, okay, so 12 over 5 times 1 over 1 minus 4/5 common ratio, which is just going to give me 12. 1 minus 4/5 is 1/5. 1 divided by 1/5 is 5, times 12/5 is 12, which is clearly not 6 times 3 plus 4 plus 5. So let me clear off all this stuff. So all this stuff was just an example. Alright. Next thing I noticed was this. There are lots of Pythagorean triples constructed by any odd side length, any odd short side length. So for instance, well, except for 1. 1 is, oh sorry, 1, 1, 2. Yeah, sorry. No, not 1, 1, 2. That's not a Pythagorean triple. So 1 does not create one. But 3 squared is 9. And 9 is 4 plus 5. Which means that 3 squared plus 4 squared is going to be 5 squared. So 5 squared is 25. And what happens is this. When you increase a perfect square, when you increase something by 1, so we get 4 and 5. When I go from 12 squared to 13 squared, I add on 12 and I add on 13. That's the trick here. 5 squared is 25. 25 is equal to the two adjacent integers that add up to 25 are 12 and 13, so 12 plus 13. That's going to give me that 5 squared plus 12 squared equals 13 squared. And I can continue down this merry path until I get a solution. But I can actually use some more information now. So in here we can see any of the odd numbers, any odd number here, I can make a Pythagorean triple. I need a Pythagorean triple that's not like 6, 8, 10. Those aren't relatively prime. So I will call this side B, this side A, this side C. And as we saw earlier, the first term in here is going to be found by B times, let me make sure I'm doing this correctly, A over C. But we also saw this. This B is like the 3 or the 5. And so, in here, I can get an A value and a C value simply from this rule. So A is going to be B squared minus 1 over B squared minus 1 over 2. And C is going to be this B squared plus 1 over 2. 25 plus 1 is 26, divided by 2 is 13. 25 minus 1 is 24, over 2 is 12. And so instead of just sort of continuing and continuing until I finally get the one that works out, which actually wouldn't take too long, it's actually how I did it the first time, I could actually go through and say, okay, the sum here, well, the first term is going to be B times A over C. So I have B times A over C. The common ratio is going to be, let's see, common ratio here is going to be this A over C. Like in the first case we had 4 over 5 as the common ratio. So I'm going to have 1 over 1 minus A over C. Now, A and C are separated by 1 unit for all of these cases, so this is going to equal BA over C times 1 over C. And so in this, these cancel. And using what we saw here, I can change out the A for B squared minus 1 over 2, so I get the sum of all these yellows is going to be B times B squared minus 1 over 2. And I want to make that equal to 6 times the perimeter. Well, the perimeter is going to be B plus A plus C. And in here, so let me make sure I've got this correct. So I do B plus A plus C. That's going to give me A plus C is going to be B squared. So I will get 6 times B plus B squared. Which is the same thing as B times 1 plus B. And I can cancel out the B's. I can multiply through by 2. I'm running short of room, but I will get b squared minus 1 equals 12 plus 12b, which gives me b squared minus 12b minus 13 equals 0. Factor that. That's actually really easy to factor. So that gives me b minus 13 times b plus 1 equals 0. The solutions are 13 and negative 1. Negative 1 cannot be a side length in a triangle, so the answer for this, I'm going to use b equals 13. And that would give me 13. 13 squared is 169. 169 is 84 plus 85. And 84 plus 85 is 169 plus 13. So let me write that out. 84 plus 85 plus 13 will give me 182. Double check to make sure I did that addition correctly. That'd be very dumb thing to do at the end is mess up the addition. Okay, and what I originally did, I just kept on going up 3, 5, 7, 9, 11, 13, and I just worked my way up to it instead of going towards this. But this is a nice way to sort of solve through it. Feel free to put any questions in the comments, and I'll get back to some more of these maybe tomorrow.